So today we will continue with chapter 13 on vibrations and simple harmonic motion. Let's remember what we took yesterday. So we are mostly interested in this mass spring system, okay? Where there is a mass attached to a spring, we elongate it or we compress it. It doesn't matter what is the original situation. Let's take that first, we elongate it until it reaches x equal x maximum. Okay, and then we release it from rest. So if we release it from rest, it means v equal to 0 at this maximum position. How much will A be? It will be A maximum, because remember, at this position, there will be lots of tension pulling the string to compress. So there will be high value of acceleration, because tension and acceleration are related together by Newton's second law, tension equal ma. Now, at equilibrium, x will be 0. There will be no elongation, there will be no compression. So x will be 0. But the spring is coming with a very high, with loss of energy that it will build up in speed. So at equilibrium position at x equals 0, v will be v maximum. The acceleration, however, will be 0. Why? Because at equilibrium, there is no tension, so there is no acceleration. Then it will continue to compress the spring until it reaches x equal minus x maximum. Again, at this point, it will stop, so v will be 0, and a will be a maximum, because now the spring is compressed to the highest position. Then it will go back to the equilibrium, then back to the x equal maximum, then back to 0, then x equal minus x maximum, then x equals 0, then x equal plus x maximum, etc. And if the friction is neglected, then this will continue forever in this regime. Okay. I just want to say one thing. We will not work on it today, but I want you to keep it in your mind. It's from the previous lesson. It's about mechanical energy. I want you to remember that when there is no friction, mechanical energy will be conserved. So mechanical energy here at maximum compression will be equal to mechanical energy at equilibrium position, will be equal to mechanical energy at minimum compression, and will be equal to mechanical energy at any other position. I just want you to keep this in mind. We are not going to work on this today, but we are going to work on this tomorrow. Okay. Now, what else we learned yesterday? We learned that there is a period, which is the time for one full cycle. So let's look at this. It starts at x maximum, it goes to 0, it goes to minus x maximum, it's back to 0, it's back to x maximum. From x maximum to x maximum, this is one full cycle. So if I know the time from this position to this position, it means this is the period. Okay, it doesn't always start from x equal x maximum. It may start from x equal minus x maximum. So then the one full cycle will be from x equal minus x maximum to 0 to x equal x maximum to 0 to x equal minus x maximum. This will be one full period. So period is time for one complete cycle. The unit for period, it's the unit of time, it's second. F, it's the frequency. It is 1 over period. It's how many cycles you perform in 1 second. Okay, it's the number of cycles per unit time, which is per second. Okay, and the unit for frequency is hertz. So per unit time, or we say number of cycles per second. Okay, the unit for frequency is hertz. Now, what is omega? Omega is another unit of frequency. So it is F, but I multiply it by 2 pi. So these we took yesterday. A, the amplitude, it is x maximum. Okay, this was, oh, we also took it yesterday. We have A, it is the amplitude, or it is x maximum. X maximum. Okay. Okay. Now, In the case of mass spring system, so these things T equal period F equal 1 over T, these can be applied to anything. And yesterday we worked with examples like the bee wing, which is the wing of a bee flying. But we are mostly interested in this mass spring system. For this particular case of mass spring system, I want you to memorize the following equations. Omega, it is 2 pi F, but it's also square root of K over M. Okay, so omega is square root of K over M. So if I know the spring constant of the spring, and I know the mass of the object I'm attaching here, omega will be square root of K over M. Okay? We need to memorize this. So if I know this, again, if I know the spring constant of the spring and I know the mass of the particle I'm dealing with, so omega is square root of K over M. Okay? X maximum is nothing but the amplitude. So it is the amplitude of oscillation. V maximum, it is omega A, so it is velocity at the equilibrium position. Velocity at the equilibrium position is V maximum, it is equal to omega A. A maximum is omega square A, okay? And A maximum happens at X maximum and at minus X maximum. Okay, so let's remember this. So V maximum happens at equilibrium. A maximum happens at X maximum and at minus X maximum. Okay, so these you need to keep in mind. Omega for a mass spring constant, it's square root of K over M, and it's also K 2 pi F. So if I know the F, I just multiply it. If I don't know it, I use this formula. Let's do some exercises. Before the exercise, so graphical representation of position in simple harmonic motion. Okay, so this type of motion is called simple harmonic motion. And if we want to draw this, like if you remember, for a horizontal motion, the X was a straight line, right? The trajectory. For a projectile, it was this type of motion. Now, for simple harmonic motion, for this spring, it starts, for example, from 0. So let's say that it starts from equilibrium. Then it goes to maximum. Then it goes back to 0. Then it goes to minimum, which is minus X maximum. Then it goes to 0. Then it goes to maximum. Then it goes to 0. Then it goes to minus X maximum. Then it goes to 0. Okay? So this is how it moves. It's like a wave. Okay? Now, from this graph, for example, we can get two pieces of information, okay? The first piece of information is the amplitude. We already know that the amplitude is X maximum. So where is X maximum? It is 0.5. So from the graph, we get that A is 0.5. The unit is meter because they're giving me here, X is in meter, okay? Now, the period is for one complete cycle. You can take it from wherever you want. You can take it from here to here, for example. You can say it's from here to here, okay? This is for what seconds? You can take it from the head to the head or the peak to the peak. This is also, here it is 5, here it is 1, so it's 5 minus 1, it's also 4 seconds. You can take it from wherever you want. You can take it from here to here. This is 8. This is 6. Is this 8? Wait, 4, 5, 6, 7. So this is 7 and this is 3. So 7 minus 3 is also 4. So you can decide to take the period from wherever you want because here I have time. Okay, so time for one complete cycle. You take time for one complete cycle. Now, if I know the T, then I know the frequency, which is 1 over T. If I know frequency, then I know omega, which is 2 pi F. If I know omega and I have A, then I know V maximum, it is omega A. If I know omega and I know A, then I get A maximum, which is omega square A. So again, let's write this. If I know F, if I know T, then I know F equal 1 over T. If I know F, then I know omega, which is 2 pi F. I know omega and A, then I know V maximum, which is omega A. And if I know omega and A again, then I know A maximum, which is omega squared times A. So if I have the graph, I can get all the information I need. I can get the A and the T. Then from the A and the T, I can get all these. Okay? Oh, now let's start with the first exercise. It's from your booklet. It's from your booklet. Exercise 2, page 42. An air track glider oscillates horizontally on a spring at a frequency of 0.5 hertz. So they're giving me the frequency equals 0.5 hertz. Suppose the glider is pulled to the right of its equilibrium position by 12 centimeters. Okay, so if you want to imagine this, the scenario is like this. You have the spring. Okay, this is the equilibrium position. And what happened is that we pulled it by 12 centimeters from the equilibrium position. Okay, so now we have the object here. Okay, and then it is released. So we start here, okay, and then it is released. When they say release, it means velocity equal V at this, it means released from rest. Okay, so velocity here is 0. Okay, where will be the glider 1 second after release? They're giving me the graph. Where will the glider be 1 second after its release? So I come, this is here X in centimeter, this is here T in seconds. They want it after 1 second. So I come, this is at 0 seconds, 0.5 seconds, 1 second. So this is what they are asking for, okay? What's the position here? What's the position here? The position is down here, right? So at T equal 1 second, X is equal minus 12. So this is part A. At T equal 1 second, X equal 12 centimeter. We can keep it in centimeter if we are not going to calculate anything else. Okay, now part B. What is its velocity at this point? Sorry, here it is minus 12, right? It is minus 12 centimeters here from the graph. At T equal 1 second, minus 12 centimeters. What will be the velocity at this point? Here you have to imagine that it is elongated, compressed until it reaches maximum compression at minus 12. What is the velocity at maximum compression? Remember, it will stop and then elongates again. It will stop, it means the velocity will be 0. Okay, so these you have to remember. So let's go back, for example, here, because you can see it clearly. At X equal minus X maximum, V equal to 0. Okay, you have to keep this information in mind. You can find the solution here. Now, another graph, and here I put all the equations we're going to use. The adjacent figure shows data for the vertical position of the wingtip of a bird. Okay, this is information for the wingtip of a bird. So we cannot use the KM and these things. Find the initial position Y0. So the initial position, it means at T equal 0. So at T equals 0, I come here. At T equals 0. Okay, where is the X? Where is the Y? In this case, they call it Y. At T equals 0, Y equal 40. So at T equals 0, Y equal 40 millimeter. which is equal 0.04 meter. It's always a good practice to change into SI units. Okay, this is Y0, part B. So this is here, part A. Part B, find the amplitude A. So you come to the graph. What is the amplitude? The amplitude is the maximum position. What's the maximum position? So the amplitude is X maximum, which is the maximum position is 40 millimeter. Again, 0.04 meter. Just for you to remember, from millimeter to meter equal meter divided by 1,000. So I divide by 1,000, okay? Part C, determine the period. Determine the period. So I come, period is along the time axis. So you can take from peak to peak. Let's take from peak to peak. It's always the easiest. Let's take it in another color. From peak to peak, how much is this? This is the period. It is from 0 to 40. So C period equal 40. 40 what here? Millisecond. So millisecond. So again, this is 0.04 seconds. Okay. All these are from the graph. I'm not doing any calculations. Okay. Let's continue. Now we want to deduce the frequency. We deduce the frequency. Frequency is deduce. It means I have to use the previous part. So frequency is 1 over T, which is 1 over 0.04. And this gives me 25 hertz. Okay, the unit of frequency is hertz. Part E. What is the maximum acceleration of the wingtips? I come here. What is A maximum? A maximum is omega square times A, okay, which is equal. A, I have it. It is 0.04, the amplitude. Omega, I don't have it, but I can calculate it. From what? I calculate it from F. So it is 2 pi F, right? 2 pi F square times amplitude. Let me. Okay, so now I come and just put the numbers. So this is equal to 2 times pi, which is a 3.14, times F, which is 25. Okay, all of it square times amplitude, which we have is 0.04. This gives me 157 square times 0.04, and this gives me 986 meter per second square. Just remember that this is acceleration, so its unit is meter per second square. Let's do one more exercise. So here you find the whole solution. The adjacent figure shows the data for the vertical position of the wingtip of, wait a second, just focus. Now let's look at here. This is exercise 6, page 44. We record as a function of time the variation of the abscissa X of the solid S connected to a free end of a spring. So this is a spring and an object attached to it. Use the graph to find x0 at time equals 0. So I come here at x at time equals 0. How much is x? X is 3 centimeter. It's here. This is at time equal to 0. So part A, at time equals 0, x equals 3 centimeter, which is equal 0.03 meter. We got this from where? From the graph. Okay, the amplitude of oscillation, also the amplitude is x maximum, which is also 3 centimeter, which is 0.03 meter. Again, from the graph. Then they want the period. They want the period. So I can take peak to peak here. Let's erase this one. So it's from here to here. This is one complete cycle, right? It was at the peak. It went to the equilibrium. It went back to the compressed, then to the equilibrium, then to the elongated. So this is one complete cycle. How much is the time for one complete cycle? It is 0.8 seconds. It is this number over here, right? It is 0.8 seconds. So the period T is 0.8 seconds. Again, from graph. Okay, now part B. Deduce the value of the frequency. Frequency is 1 over T. It's here, the highest value here. Frequency is 1 over T. So this is 1 over 0.8. And this is nothing but 1.25 hertz. Then deduce omega. Omega is equal to 2 times pi times f. It's here, omega is 2 pi f. This is equal to 2 times 3.14 times f, which is 1.25. And we get 2 times 3.14 times 1.25. We get this to be 7.85. What's the unit for omega? Just to remember, it's radian per second. Okay, part C. Part C. If the spring constant K equal 20 Newton per meter, find the mass of the solid. Okay, so here I want to use, so they give me K, I have omega, and I want to get the mass. So this is the first time we're gonna use this formula. Okay, this we only apply when we have a spring and a mass. Okay, this formula. All the others I can apply everywhere, but it's this formula is only applicable when I have a spring mass object. So let's do it here. Omega is equal to square root of K over M. Okay, omega is 7.85. The best way to get rid of the, so this is 7.85 is equal to square root of K, which is 20 divided by M. Now to get rid of the square root, I square both sides. Square both sides. So I get 7.85 square is equal to 20 over M, which gives me 7.85 square, 61.62 M equal 20 implies M equal 20 over 61.62, and this is 0.32. 5 kilograms. Okay. So we have used all these equations in all the problems we solved today. Let's say there is no problem like that. There's no exercise like that. But what if they ask us to calculate the V maximum? Okay. We will use omega A. We have omega from part B, and we have A from part A. I just multiply them and I get V maximum. What if they tell me where will V maximum be? Name one position on the graph where V maximum will be. Okay, it will be at V at x equal to 0. At x equal to 0, V will be equal V max. Okay, and at x equal maximum and minimum, A will be A max. Okay, just in case they also asked for something like this. They didn't ask, but this is extra. So that's it for today's lesson. Tomorrow we add the last bit for this lesson and we solve more exercises. Bye-bye.